Gravity might be the universe's greatest illusion. This is the profound mystery of quantum gravity, the ultimate puzzle in modern physics. For decades, scientists have struggled to unite Einstein's elegant theory of general relativity with the bizarre, probabilistic rules of the quantum world. One describes the force that sculpts galaxies, while the other governs the realm of the impossibly small. Their refusal to cooperate points to a deeper reality we have yet to uncover. By the end of this journey, you will have explored 30 of the most fascinating and groundbreaking theories that attempt to solve this cosmic riddle. We will venture into realms where space and time are woven from tiny loops, where our entire universe could be a holographic projection, and where black holes might hold the final key. What single idea about reality most challenges your intuition? Our first contender in this cosmic puzzle dares to suggest that the smooth, continuous space we take for granted is a grand illusion. This is loop quantum gravity, a theory that proposes space itself is woven from tiny, one-dimensional loops. Think of the fabric of reality not as a smooth sheet, but as an incredibly fine mesh, with each thread a billion times smaller than an atom. These loops do not exist within space, they are space. They interweave and connect to form a vast, evolving structure physicists call a spin network. This revolutionary idea solves one of the most vexing problems in physics, the dreaded singularity. In Einstein's general relativity, the center of a black hole and the moment of the Big Bang are points of infinite density where the laws of physics simply break down. But in the world of loop quantum gravity, space cannot be squeezed into an infinitely small point. Just as you can only divide a material into individual atoms, you can only divide space down to these fundamental loops. This means the Big Bang was not a true beginning, but potentially a great bounce from a previous universe that had collapsed. Pioneered by thinkers like Carlo Rovelli and Lee Smolin, this theory gives us a powerful new vocabulary for describing the cosmos. To visualize how this network changes over time, we can picture a spin foam, a frothing, bubbling structure where the spin network evolves, representing the passage of time itself. It is a breathtaking vision, a universe built not from particles in a void, but from the very relationships between these elemental loops of space. But what if the fundamental ingredients of reality are not tiny loops of space, but something even more bizarre? This brings us to the most famous and perhaps most extravagant contender in the quest for quantum gravity, string theory. It proposes a beautifully simple yet deeply strange core idea. The universe is not made of point-like particles, but of unimaginably small, vibrating strings. Each string is so tiny that if an atom were the size of our solar system, a string would be no larger than a tree on Earth. The magic lies in their vibration. Just as a single violin string can produce different notes depending on how it is plucked, these cosmic strings vibrate in distinct patterns. One specific resonance might create an electron, another a quark, and yet another a photon of light. In this symphony of strings, every particle is simply a different note in the cosmic composition. The theory's most profound achievement is how it naturally includes gravity. One particular vibrational pattern of the string would produce the long-sought graviton, the hypothetical particle that carries the gravitational force. For the first time, gravity is not a foreign concept awkwardly forced into the quantum world, but an inevitable and beautiful consequence of the string's music. Yet, this elegance comes at a cost, a requirement that reshapes our view of reality. The mathematics of string theory only works if the universe has more than the 3 spatial dimensions we experience. It demands a cosmos of 10 or even 11 dimensions. So where are these extra dimensions? Theorists suggest they are curled up or compactified into shapes so incredibly small that we cannot perceive them. These shapes are known as Calabi-Yau manifolds, intricate, multi-dimensional forms that look like fantastical abstract sculptures. The specific way these manifolds are folded determines the properties of our universe, from the number of particle types to the strength of the forces themselves. It is a breathtaking vision where the entire cosmic order hinges on the geometry of hidden realms. Despite its compelling mathematical beauty, string theory faces a significant challenge. It has yet to make a single prediction that can be tested with our current experiments. We are asked to believe in a universe of unseen strings and hidden dimensions, a grand hypothesis waiting for its crucial moment of verification. While string theory imagines vibrating strings in hidden dimensions, another powerful idea takes a completely different path. It asks a disarmingly simple question. What if we could build the universe from the ground up, piece by piece, like a cosmic mosaic? This is the promise of Causal Dynamical Triangulations, or CDT. Forget strings or loops for a moment. This theory proposes that the fundamental building blocks of reality are tiny, simple geometric shapes, specifically tiny triangles. In this digital approach to quantum gravity, the smooth, continuous spacetime of Einstein is not a starting point, but an end result. It is an illusion that emerges from a vast, chaotic sea of these microscopic pieces. Think of it like a giant digital photograph. Up close, you only see individual pixels, blocks of color with sharp edges. But as you zoom out, those pixels blend together to form a smooth, recognizable image. CDT suggests our four-dimensional universe works in exactly the same way. The pixels are these tiny triangular building blocks, and they snap together following one crucial rule: causality. This means each new block must connect in a way that respects the flow of time. An effect can never come before its cause, even at this most fundamental level. This causal rule is the glue that holds the emerging universe together and prevents it from dissolving into pure chaos. Through powerful computer simulations, physicists can watch this universe being built. They start with a random, foaming jumble of these triangular pieces, a state often called quantum foam. It is a turbulent, high-energy mess with no discernible order, where time and space have no clear meaning. Then they let the simulation run, allowing the pieces to connect and reconfigure according to the simple causal rules. Something remarkable happens. From this primordial chaos, a structure begins to crystallize. The simulation spontaneously forms a smooth, four-dimensional spacetime, complete with the three spatial dimensions and one time dimension we experience every day. It is as if you shook a bag of random Lego bricks for long enough, and they suddenly assembled themselves into a perfect, recognizable model of a house. This emergence of our familiar reality from a disordered quantum beginning is one of the most compelling successes of this approach. It shows us that the order of our cosmos might not be written into the universe's foundational code, but could be a natural, almost inevitable outcome of simple building blocks following simple rules. The universe, in this view, is the ultimate self-assembling structure. Another path to quantum gravity asks us to look at the problem from an entirely new angle. Suppose the problem is not with gravity itself, but with our mathematical tools. This is the promise of asymptotic safety. It proposes that gravity, just like the other fundamental forces, can be described as a quantum field theory, but one with a very special property. Its strength remains perfectly finite at all energy scales, no matter how high you go. To understand why this is so revolutionary, picture a scientist trying to calculate what happens when two particles gravitationally interact at impossibly high energies. In standard approaches, the mathematics breaks down, producing results that are literally infinite, a clear sign that the theory is incomplete. But in an asymptotically safe theory of gravity, this does not happen. The strength of the gravitational force, what physicists call the coupling constant, is kept in check. It is guided by an invisible hand that prevents it from ever spiraling out of control into infinity. The universe, in this view, has a built-in safety mechanism for gravity. The key to this mechanism lies in a powerful concept known as the renormalization group. This is a mathematical way of understanding how a theory changes when you look at it at different scales or energies. Think of it like using a camera with a zoom lens. When you zoom out to look at the large-scale universe, gravity appears as Einstein described it, a gentle curvature of spacetime. But as you zoom into the most extreme high-energy realms, the theory must transform. For gravity to be asymptotically safe, its parameters, its very essence, must flow toward a special destination called a fixed point. Imagine a complex landscape of hills and valleys where the ball representing the theory of gravity is rolling. In most theories, the ball rolls wildly downhill into a ravine of infinities and the calculation is lost. But in an asymptotically safe scenario, the ball is guided directly to a stable plateau, a fixed point where it comes to rest. At this point, the theory is well behaved and predictable, even under the most extreme conditions we can conceive, like the center of a black hole or the first instant of the Big Bang. While this idea is highly technical and the search for conclusive proof continues, it offers a beautifully minimalist solution. It suggests we may not need extra dimensions or fundamental strings to tame gravity. The universe's underlying geometry might be all we need if only we can learn to map its deepest contours. But what if we strip reality down to its most essential ingredient, the simple concept of cause and effect? This is the radical proposition of causal set theory. It suggests that the true foundation of our universe is not a fabric of space or a collection of vibrating strings, but a vast collection of discrete events, the atoms of spacetime itself. In this view, each event is a fundamental point of reality, and the only thing that truly matters is the causal relationship between them. If one event can influence another, a link is formed. The entire history of the cosmos can be imagined as an immense, growing network of points connected by arrows, a cosmic family tree of cause and effect. This simple, elegant structure is known as a causal set. The smooth, continuous spacetime we experience, with its gentle curves and reliable geometry, is not the fundamental reality. It is an illusion, a large-scale average that emerges from this chaotic, granular underworld. Much like a smooth, continuous material emerges from the frenetic motion of its individual atoms. One of the theory's most profound implications is its treatment of time. In many physical models, time is just another dimension, a static coordinate where the past, present, and future all exist simultaneously. But in causal set theory, time is real and dynamic. The universe is the process of this network growing, with new events constantly being born from the causal history of the old. This inherent directionality, this relentless growth from cause to effect, provides a natural explanation for the arrow of time and elegantly avoids the mind-bending paradoxes of time travel. Since you cannot have an effect before its cause, the fundamental structure of reality simply forbids the creation of closed time-like curves, those theoretical loops that could allow someone to travel back into their own past. The geometry of our world, the distances we measure and the durations we feel are not primary. They are derived from the pattern of connections within this causal network. A simple analogy can help. Imagine you have a vast, dark sheet of paper and you begin to sprinkle tiny dots onto it at random. Each dot is an event. You then draw an arrow from one dot to another if the first could have influenced the second. You do not start with the paper. The paper is an illusion that only appears once you have enough dots and arrows. The resulting web, a seemingly chaotic spray of points, secretly contains within its connection patterns all the information needed to reconstruct a full, four-dimensional universe. This is the beautiful, minimalist promise of causal set theory, that all of reality is encoded not in things, but in the relationships between them. The very nature of gravity as a fundamental force is now being called into question. What if the pull you feel holding you to the Earth is not a force at all, but a kind of cosmic illusion, a side effect of a deeper, more fundamental principle? This is the radical proposition of physicist Eric Verland and his theory of entropic gravity. It suggests that gravity is not a fundamental interaction woven into the fabric of the universe, but an emergent phenomenon. It arises from the way information and entropy are distributed throughout space. To grasp this, think about the concept of temperature. When you feel that a cup of coffee is hot, you are not sensing a fundamental substance called heat. You are feeling the collective, frenetic motion of trillions of water molecules. The property of temperature emerges from their microscopic behavior. Verland proposes that gravity works in a similar way. It emerges from the behavior of the microscopic constituents of spacetime itself, whatever they may be. In this view, the gravitational force we measure is actually an entropic force. It is the universe's tendency to maximize its disorder, or entropy. Imagine a simple physical system like a polymer chain, a long, wiggly molecule floating in water. If you try to stretch the chain out, pulling it straight, you are forcing it into a very ordered, low entropy state. The chain will resist. It will pull back, not because of some fundamental force of elasticity, but because the system is driven to return to a more probable, wiggly, high entropy state. That pull is an entropic force. Now apply this logic to the cosmos. According to Verland, when a massive object like a star sits in space, it influences the entropy of the surrounding spacetime microstructure. The information content of space is rearranged. When another object, like a planet, moves into this region, the natural tendency for the entire system to maximize its entropy creates a perceived pull toward the star. The planet is not being pulled by a force, it is being guided as if down a slope by the natural gravitational gradient of increasing entropy. This is not just a philosophical shift, it has stunning physical consequences. One of the greatest mysteries in modern cosmology is dark energy, the mysterious phenomenon causing the universe's expansion to accelerate. In Verland's emergent gravity, dark energy is not a strange new substance. It is a natural outcome of the theory. The way the entropy and information of empty space scale with volume automatically produces an effect that mimics dark energy, potentially solving one of physics' biggest puzzles without inventing anything new. This idea turns our understanding of reality upside down. Gravity, the force that sculpts galaxies and holds our feet to the ground, may be a statistical mirage, a shadow cast by the relentless drive of the universe toward disorder. It suggests that the most fundamental aspects of our world are not forces or fields, but information itself. This concept of gravity as an emergent phenomenon finds its ultimate expression in one of the most mind-bending ideas in all of physics. The holographic principle dares to suggest that our experience of a rich, three-dimensional universe is a magnificent illusion. It proposes that all the information needed to describe everything within a volume of space, every star, every planet, every person, is actually encoded on a distant, two-dimensional surface that surrounds it. We may be living inside a cosmic projection, a hologram of staggering complexity. The origin of this astonishing idea lies in the paradoxical nature of black holes. In the 1970s, physicist Jacob Bekenstein made a revolutionary connection. He realized that a black hole's entropy, which is a measure of its information content or disorder, is not proportional to its volume as one might intuitively expect. Instead, it is precisely proportional to the surface area of its event horizon. This was a profound clue. In any ordinary system, like a box of gas, the maximum possible entropy, the number of ways you can arrange its constituents, grows with the volume of the box. A bigger box can hold more disorder, but a black hole, the most efficient information compressor in the universe, defies this rule. Its information capacity is defined by its surface area. This implies that all the information about what fell into the black hole, every atom and every photon, is not lost inside the inaccessible interior. It is somehow painted onto the two-dimensional surface of the horizon. The three-dimensional interior is, in a sense, redundant. The real description of the black hole's contents lies on its boundary. The holographic principle boldly extends this black hole logic to the entire cosmos. It suggests that our universe itself operates by the same rules. The room you are in, the air you breathe, the device you are using to listen to this, all of it could be described by a theory that exists on a vast, remote, two-dimensional surface at the edge of the observable universe. We are not the source of the projection, we are the projection itself. Think of a common hologram on a credit card. The flat, shiny surface contains etched lines that, when illuminated with light, project a stunning three-dimensional image that appears to float in space. The holographic principle argues that our reality is a far more sophisticated version of this. The entire universe, with its galaxies, its forces, and the flow of time, is a projection from a two-dimensional information field. This is not just a philosophical curiosity, it has staggering implications for the nature of reality. It means that the fundamental building blocks of the cosmos are not located in the space around us, but on a distant boundary we cannot see. It suggests a deep and profound connection between gravity, described by general relativity in the bulk of space, and quantum field theories that live on the boundary. In this view, gravity itself is the thermodynamic force that emerges from the holographic encoding of information, a direct link to the idea of entropic gravity. If this principle is true, then the intuitive, concrete reality we experience every day is the grandest illusion of all, a seamless holographic movie generated from the simplest possible ingredients, information written on the surface of the world. The elegant mathematics of string theory pointed toward a universe with extra dimensions, but another profound idea was already paving the way. Supergravity emerged as a breathtakingly beautiful fusion, a marriage between the cosmic force of gravity and a powerful quantum symmetry known as supersymmetry. Supersymmetry proposes a deep and fundamental partnership at the heart of reality. It suggests that for every known type of particle, there exists a hidden, unseen superpartner. The particles that make up matter, like electrons and quarks, are known as fermions. The particles that carry forces, like photons and gluons, are called bosons. Supersymmetry creates a bridge between these two families, transforming a fermion into a boson and vice versa. It is a cosmic dance where matter and force are two sides of the same coin. When physicists applied this powerful symmetry to Einstein's theory of gravity, something remarkable happened. The mathematics demanded a new particle, a superpartner for the hypothetical graviton. This new particle was named the gravitino. If the graviton is the quantum particle that carries the force of gravity, the gravitino is its fermionic twin, a particle of spin 3/2 that would mix the properties of gravity with those of matter in a completely new way. The emergence of supergravity was a monumental step. It showed for the first time that a supersymmetric version of general relativity was not only possible but also stunningly elegant. The equations became more balanced and mathematically tractable, resolving some of the thorniest infinities that had plagued previous attempts to quantize gravity. This mathematical harmony made it a crucial stepping stone, directly inspiring the development of superstring theory, which incorporated supersymmetry into its very core. The predictions of supergravity are as profound as its origins. It implies that the universe is teeming with a whole new class of particles we have yet to detect. Every electron would have a superpartner called a selectron. Every quark would have a squark, and of course the graviton would have its gravitino. This hidden population of superpartners could solve one of the greatest mysteries in physics, the nature of dark matter. The lightest of these superpartners could be stable, invisible, and pervasive, floating through the cosmos and providing the gravitational glue that holds galaxies together. Yet, for all its theoretical promise, supergravity faces a stark experimental challenge. To find these particles, scientists have built the most powerful microscopes in history, colossal machines like the Large Hadron Collider. Inside its 17-mile circular tunnel, protons are accelerated to nearly the speed of light and smashed together, recreating the energetic conditions of the early universe. Sophisticated detectors, like giant digital cameras weighing thousands of tons, capture the aftermath of these collisions, looking for any telltale sign of a new particle, a selectron or a gravitino flashing into existence for a fraction of a second. So far, the detectors have remained silent. No definitive signal for any superpartner has been found. This non-observation forces physicists to reconsider. Perhaps supergravity is not the final answer, or perhaps these superpartners are far heavier than initially hoped, hiding just beyond our current reach. The search continues, a high-stakes hunt for a hidden symmetry that could either confirm one of our most elegant theories or force us to imagine an even deeper truth. The rigid coordinates of a map dissolve into a quantum haze. This is the startling vision of non-commutative geometry, a theory proposing that the very stage of reality becomes blurry at its most fundamental level. In our everyday world, the order of operations does not matter. You can measure the position of a car on a highway and then its speed, or its speed and then its position, and you will get the same result. The measurements commute, but in the quantum realm, this simple logic breaks down. Heisenberg's uncertainty principle tells us we cannot know both the exact position and the exact momentum of a particle at the same time. Non-commutative geometry extends this profound uncertainty to spacetime itself. It suggests that at the unimaginably small Planck scale, the coordinates of space and time no longer commute. Measuring position in one direction and then another might yield a different result than if you reversed the order. This fundamental fuzziness means that the concept of a sharp, pinpoint location loses all meaning. Spacetime becomes an ethereal, uncertain foam, a quantum cloud where the very notion of here and now is inherently blurred. To visualize this, think of a digital photograph. When you zoom in as far as you can, you eventually see the individual pixels. Now, imagine if those pixels themselves were shimmering and unstable, flickering between different states. You could not say precisely which pixel was which color at a given instant. That is the kind of fuzzy, non-commutative canvas this theory paints for the fabric of reality. Yet this is not just a philosophical statement about spacetime. The true power of non-commutative geometry lies in its ability to reframe the entire universe of particles and forces. In this view, the bizarre properties of the quantum world are not tacked onto spacetime. They are a direct expression of its fuzzy, non-commutative nature. The theory provides a new geometric language where the forces of nature, like the electromagnetic force and the nuclear forces, are not separate entities. They emerge naturally from the intricate, convoluted shape of this quantum spacetime. The different types of elementary particles, from electrons to neutrinos, are not just scattered occupants of space. They are like the different resonant notes of a strangely shaped musical instrument, where the instrument itself is the fuzzy geometry of the world. This approach offers a breathtakingly unified picture. It does not add new dimensions like string theory, but instead deforms the familiar mathematics of geometry to naturally include the entire standard model of particle physics. The forces and particles we have spent decades discovering in colossal particle accelerators are all seen as shadows cast by the deep, non-commutative geometry of spacetime. It is a vision where the universe is not built in a geometric arena, but is that geometry in its most exotic and fundamental form. This broader vision of emergence transforms gravity from a fundamental actor into a collective performance. The stage of spacetime itself may not be a foundational backdrop, but a spectacular illusion that crystallizes from a more basic, pre-geometric reality. Imagine the surface of a flowing river. The water is made of countless individual molecules colliding and interacting. Yet from this chaos, large-scale patterns emerge like whirlpools and currents. We can describe the river's flow using the smooth, continuous equations of fluid dynamics without ever mentioning a single water molecule. In this analogy, the river's flow is like space-time and gravity. It is a powerful, effective description of a collective behavior, but not the fundamental truth. The real story is happening at the level of the molecules, the pre-geometric entities that have no inherent concept of space or time as we know them. This idea finds a stunning example in the concept of an acoustic metric. Consider a fluid flowing faster and faster until it surpasses the speed of sound within that fluid. Any sound wave trying to travel upstream against this supersonic flow would be swept backward, unable to make any headway. This creates a sonic horizon, a point of no return for sound, which behaves with mathematical precision exactly like the event horizon of a black hole. From the perspective of a sound wave, the fluid's flow has created a curved spacetime geometry, complete with a trap from which it cannot escape. Yet, we know there is no real gravity here, no warping of fundamental spacetime. The geometry is emergent, a direct consequence of the collective motion of the fluid's atoms. This analogy powerfully suggests that our own universe's gravitational fields and black holes could be similar illusions. They may not be features of a fundamental spacetime, but rather dynamic patterns that arise from the interactions of countless underlying constituents. What we perceive as the force of gravity could be the irresistible tendency of the system to evolve toward a state of higher probability, a thermodynamic push rather than a geometric pull. The very fabric of space and the flow of time may be the universe's most successful collective hallucination, a seamless reality generated by something far stranger and more fundamental. Light rays may be the true atoms of reality. This is the elegant and radical proposition of twistor theory, conceived by the renowned physicist Roger Penrose. It challenges the very bedrock of our physical descriptions. For centuries, we have built physics on the idea of spacetime points, precise locations defined by coordinates of here and now. But Penrose asked a deeper question. What if these points are not fundamental? What if the true primary elements are the paths of light itself? In twistor theory, the fundamental objects are not points but twistors. A twistor is a complex mathematical object that geometrically represents a single, fundamental light ray, complete with its direction, energy, and spin. It is a universe built not from places, but from the very act of propagation, from the threads of light that weave the cosmos together. In this breathtakingly different framework, our familiar four-dimensional spacetime is not the starting point. It is a secondary, derived concept that emerges from the rich, interconnected web of these twistors. The geometry of twistor space is a higher dimensional realm where the laws of physics can be rewritten in a strikingly simple and elegant form. One of the theory's most profound successes lies in the complex world of particle interactions. When subatomic particles collide and scatter in powerful accelerators, calculating the probabilities of their outcomes is notoriously difficult. The mathematics of traditional quantum field theory involves thousands of intricate cancelling diagrams. Yet, when these same processes are translated into the language of twistor space, the calculations often collapse into stunningly simple and beautiful geometric forms. Intricate particle scattering amplitudes, which once required pages of algebra, can be represented by the volume of a multifaceted geometric shape in twistor space. This is not just a mathematical shortcut, it is a hint that twistor theory is tapping into a deeper, more natural language for physics. The theory's geometric heart also suggests a powerful bridge between the worlds of quantum mechanics and gravity. By building reality from light rays, concepts that are separate and awkward in standard physics become unified in twistor space. The theory hints at a way to describe gravitational phenomena, like the ripples of gravitational waves, as natural properties of this twisted geometry, offering a potential path toward a seamless quantum theory of gravity. While it remains a work in progress, the influence of twistor theory is vast. Its geometric insights have deeply enriched other approaches, particularly string theory, where the twistor-inspired methods for calculating scattering amplitudes have been adopted to solve previously intractable problems. It paints a picture of the cosmos as a tapestry woven from threads of light, a geometric vision where the universe's deepest laws are written not in the language of location, but in the language of connection and propagation. These atoms of space are not static, they must speak to one another. Group field theory takes the silent, frozen spin networks of loop quantum gravity and gives them a voice, transforming them from a static map into a living, breathing process. Imagine if the universe's fundamental building blocks were not merely connected, but constantly in conversation, buzzing with quantum energy. In this framework, the tiny loops or atoms of space are not just there, they can be created and annihilated, popping in and out of existence. This is a quantum field theory for spacetime itself, where the basic entities are not particles in space, but the very quanta of geometry. The dynamics of the cosmos are written in the language of their interactions. Think of a vast cosmic marketplace. Each vendor represents an atom of space, and the goods they trade are geometric information, angles, and volumes. When these vendors interact, exchanging their information, the collective hum of the marketplace begins to generate the very structure of the city around it. The streets, the buildings, the flow of traffic all emerge from these countless individual transactions. In the same way, group field theory proposes that smooth, four-dimensional spacetime is not a given. It is the large-scale, stable pattern that crystallizes from the frenetic quantum trading between these fundamental geometric atoms. The theory's mathematical engine is a particular kind of field equation, one that governs how these atoms of space can bond, merge, or split apart. This process is visualized as a complex, evolving graph, a foam of possibilities where space is constantly being rewoven. When a high enough density of these atoms interact in just the right way, they can undergo a dramatic phase transition, much like water vapor cooling into a droplet of liquid. In the cosmic context, this phase transition is the birth of our universe as we know it, a moment when the chaotic quantum foam of geometry settled into the stable, classical spacetime that allows for galaxies, stars, and life. This powerful framework does not exist in isolation. It forges deep bridges to other cutting-edge ideas. The intricate networks describing these interacting atoms are formally known as tensor networks, which are also the secret language of the holographic principle. The way information is stored and processed in a group field theory, network mirrors how a lower dimensional boundary can encode a higher dimensional reality. This suggests a profound unity, that the emergence of spacetime from quantum grains and the holographic nature of our universe may be two different perspectives on the same magnificent truth. We are not just made of stardust, but of a dynamic, conversational geometry, a cosmic process speaking itself into existence. A dramatic paradox is tearing at the very foundations of physics, born from the irreconcilable clash between general relativity and quantum mechanics. It is the black hole information paradox, and its implications are so severe that they threaten to undermine our entire understanding of reality. The conflict centers on a single, profound question. What happens to information when it falls into a black hole? According to the sacred principles of quantum mechanics, information is eternal. It can never be truly destroyed. If you burn a book, the information within it seems lost, but in principle, a being with infinite knowledge could collect every wisp of smoke, every particle of ash, and reconstruct the entire text. The information is merely scrambled, not erased, yet general relativity paints a very different picture. When anything crosses a black hole's event horizon, it is lost to the universe forever. The black hole eventually evaporates thanks to Hawking radiation, fading away into nothingness. If that final evaporation leaves behind only random, featureless radiation, then the information about what fell in, whether it was a book, a star, or an entire civilization, is permanently erased from existence. This is an unacceptable contradiction. Physics cannot have two sets of rules, one saying information must live forever and another saying it can be completely destroyed. Something has to give. To resolve this crisis, a group of physicists proposed a shocking and violent solution: the firewall. Imagine an astronaut foolishly diving feet first into a black hole. According to Einstein's equivalence principle, this should be an uneventful, even serene journey at first. Since you are in free fall, you would feel no forces, no dramatic tearing. You would cross the event horizon without even noticing it, a point of no return that feels like empty space. But the firewall hypothesis shatters this peaceful picture. It suggests that lurking just inside the event horizon is not empty space, but a blazing wall of unimaginably high energy particles. This is not a metaphorical wall, but a literal one, a boundary of concentrated energy that would instantly incinerate the astronaut into a spray of fundamental particles long before they reach the black hole's core. The firewall acts as a cosmic shredder. It violently processes anything that falls in, scrambling its information so thoroughly that it can be encoded into the Hawking radiation leaking back out into the universe. In this brutal scenario, quantum mechanics wins. Information is preserved, but at a terrible cost. The principle of equivalence, one of the cornerstones of general relativity, is utterly violated. The event horizon is no longer a smooth, uneventful place. It becomes the most dramatic and destructive location in the entire cosmos. The very idea is so controversial because it forces physicists to choose which cherished principle to sacrifice. Do we abandon the quantum law that information must be saved, or do we break Einstein's elegant description of spacetime? The firewall paradox is not just a puzzle about black holes. It is a glaring signal, a cosmic alarm bell telling us that our current theories are fundamentally incomplete. It points directly to the need for a deeper theory of quantum gravity, one that can tell us what truly happens at the edge of reality, where spacetime itself may break down into its constituent parts. The paradox ensures that the serene black hole of Einstein's imagination is anything but peaceful. It is a raging battlefield where the laws of physics fight for supremacy. This cosmic battlefield between information and annihilation may have a hidden bridge. The ER equals EPR conjecture offers a stunningly elegant escape route from the information paradox. It proposes a deep and beautiful connection between two of physics' most famous acronyms. EPR stands for Einstein, Podolsky, and Rosen, who first highlighted the bizarre, spooky action at a distance of quantum entanglement. ER stands for Einstein and Rosen, who discovered the theoretical structure of a wormhole, a tunnel through spacetime. The conjecture boldly states that these two seemingly different phenomena are one and the same. Every pair of entangled particles is not connected by some invisible, instantaneous force. Instead, they are linked by a microscopic wormhole, a Planck-scale bridge in the fabric of reality. Imagine two electrons born together, their fates forever intertwined. In standard quantum mechanics, we say they are entangled, a ghostly correlation that defies classical intuition. But in the language of ER equals EPR, these two electrons are not just correlated. They are the two mouths of an unimaginably tiny Einstein-Rosen bridge. The spacetime between them is not flat and empty. It is geometrically woven into a short, non-traversable tunnel. This wormhole is not a passage you could ever travel through. It is smaller than a subatomic particle, a ghostly thread stitching the universe together at its most fundamental level. This geometric picture transforms our understanding of entanglement from a mysterious connection to a tangible feature of spacetime's architecture. The spooky action is not action at all, but a direct geometric link. This idea becomes profoundly powerful when applied to the black hole information paradox. Picture a black hole forming from a collapsing star. Now imagine the Hawking radiation it begins to emit. According to this conjecture, each particle of Hawking radiation that escapes becomes entangled with the black hole's interior. But if ER equals EPR is correct, that entanglement is not a formless correlation. It is a physical wormhole connecting the escaped radiation particle to the heart of the black hole itself. Information that seems trapped inside the black hole is not lost. It has a secret escape route. It can travel not faster than light, but through these microscopic spacetime tunnels, faithfully encoded into the radiation that streams out into the universe. The information is never truly behind the horizon because the geometry itself provides a backdoor. The firewall, that destructive wall of energy, might never form. The event horizon could remain a peaceful place because the information has a geometric pathway to safety. This vision paints the universe as an unimaginably complex tapestry of these tiny wormholes, a cosmic network of quantum threads that bind everything together. It suggests that the weirdest phenomenon in quantum mechanics and the most exotic object in general relativity are not just related. They are two different descriptions of the same fundamental reality, a universe where connection is woven into the very geometry of existence. Our cosmic tapestry of space and time may be woven from two fundamentally different threads. Horava-Lifshitz gravity proposes a radical surgery on Einstein's equations, suggesting that time itself is not the same as space when we probe the universe's most extreme energies. This theory dares to break one of the most sacred principles in all of physics, Lorentz invariance. This is the rule stating that the laws of physics must appear identical to all observers, no matter how fast they are moving. It is the reason a beam of light always travels at the same speed for everyone. But Peter Horava asked a daring question. What if this perfect symmetry is only an approximation, a low-energy illusion that shatters when we look closely enough? By allowing this symmetry to break at the highest energies, a regime physicists call the ultraviolet, the mathematical problems that have plagued quantum gravity for decades suddenly become tractable. The equations behave, the infinities vanish, and gravity becomes renormalizable, meaning its calculations yield sensible, finite answers. It is as if the universe has a hidden, high-energy operating system where the rules are simpler, but time operates on a different set of commands than space. This profound shift has dramatic consequences for the cosmos we see today. One of the theory's most compelling features is its potential to explain the accelerating expansion of the universe without any need for the mysterious dark energy. The different treatment of time and space at a fundamental level can naturally generate a repulsive gravitational effect on cosmic scales, pushing galaxies apart in a way that perfectly mimics the influence of dark energy. It offers a way out of one of cosmology's biggest puzzles by suggesting the answer lies not in a strange new substance, but in the very architecture of spacetime itself. The theory also paints a new picture of the universe's infancy. In the first fleeting moments after the Big Bang, the cosmos would have been dominated by this high-energy, anisotropic regime where time and space were clearly distinct. This could have led to a period of explosive, superluminal expansion without the need for a separate inflationary field, providing a powerful alternative origin story for the large-scale structure we observe. Yet, for all its promise, Horava-Lifshitz gravity faces a serious and fundamental criticism. Breaking Lorentz invariance is not a step taken lightly. This symmetry has been tested with exquisite precision in countless experiments, and it has never been found wanting. To abandon it is to challenge a cornerstone of modern physics. Critics argue that even if the symmetry is only broken at unreachably high energies, its effects might still percolate down to our everyday scales in ways we should have already detected, such as subtle variations in the speed of light for different colors. The theory walks a tightrope, offering mathematical salvation at the cost of a cherished principle, forcing us to ask which is more fundamental, the elegant symmetries we have discovered, or the calculable theory we so desperately need. Time itself may be a convenient fiction. Shape dynamics dares to reimagine Einstein's universe by proposing that space, not spacetime, is the true foundation of reality. This radical reformulation of general relativity makes a profound trade. It abandons the relativity of simultaneity, the idea that different observers can disagree on the order of events, and replaces it with a relativity of size. This is known as conformal symmetry. In this view, the absolute scale of the universe is meaningless. Only the angles and shapes between objects are fundamentally real. You could theoretically shrink the entire cosmos down to the size of a marble, and as long as every angle and geometric relationship was preserved, the physics would remain identical. It is a universe where the cosmos has no preferred yardstick, only a perfect angle-preserving geometry. This shift in perspective is not just mathematical elegance, it is a strategic move to make gravity more compatible with quantum mechanics. One of the most stubborn problems in uniting the two theories is the problem of time. In the standard quantum formalism, time is an external, absolute parameter that ticks away in the background. But in general relativity, time is dynamic and intertwined with space, its flow warped by gravity and matter. This creates a deep conflict. Shape dynamics elegantly sidesteps this entire issue. By making three-dimensional space the fundamental stage, it restores a universal, absolute time that all observers can agree upon. The dynamic, evolving geometry of the universe is then described purely by how the shapes of space change with respect to this global clock. For all its conceptual upheaval, shape dynamics is engineered to be empirically sound. It is not a rival to general relativity, but a different mathematical representation of it, like viewing a sculpture from a new angle. In almost every situation, from the orbit of planets to the bending of starlight, it produces predictions that are indistinguishable from Einstein's theory. The magic happens in its treatment of extreme scenarios. The theory offers a fresh perspective on the interior of black holes and the very first moment of the Big Bang, potentially resolving singularities without the need for exotic new physics. It suggests that the flow of time we experience so vividly could be an emergent property, a collective consequence of the universe's relentless drive to rearrange its fundamental shapes. This is not merely a different set of equations, it is a profound philosophical shift, asking us to consider that the solidity of time and the vastness of space might be shadows cast by a deeper, more timeless world of pure geometric form. The rigid geometry of spacetime may have crystallized from a formless, blazing chaos. Quantum gravity proposes that in its first moments, the universe was not a void, but a seething, hyper-connected network, a graph of pure relationship. In this primordial state, every single node of reality was directly linked to every other node. It was a state of maximum connection, a cosmic fire where the very concepts of here and there had no meaning because everything was effectively in the same place. This was a universe of pure potential, a dimensionless soup of quantum links. Then, in a flash, it cooled. As the universe expanded and its temperature plummeted, this perfect, all-to-all network underwent a dramatic phase transition, much like superheated steam freezing instantly into a structured ice crystal. The vast majority of the links between nodes snapped, leaving behind a sparse, orderly lattice. In this great cosmic freeze, our familiar three-dimensional space was born. The nodes that remained connected became our nearest neighbors in space, while the broken links relegated other points to become vast astronomical distances away. The dimensionality of our world is not fundamental. It is a memory of this ancient freezing process, an echo of how the cosmic graph lost its connections. This dynamic graph is not just a map of space, it is the source of physics itself. Each link between nodes represents a potential for interaction, a possible channel for something to happen. In the dense, early graph, particles could have propagated in any direction instantly, a concept that challenges our very idea of causality. But as the graph froze into its current, low-dimensional state, only certain paths remained open, forcing particles to follow the lattice of surviving links. This is how the speed of light may have emerged, not as a fundamental constant, but as the maximum speed information can travel along the pathways of the frozen graph. Even the forces of nature, like electromagnetism, could be guests at this geometric feast. The different patterns of vibration across this network, like different collective motions in a complex mesh, could naturally give rise to what we perceive as gauge fields, the fundamental carriers of force. A photon could be a specific, shimmering wave traveling across the lattice of the universe. This model offers a breathtakingly simple origin for one of physics' most sacred principles, Lorentz invariance, the idea that the laws of physics are the same for all moving observers. It emerges not as a foundational rule, but as a large-scale property of the graph's structure. If the network is arranged in just the right way from the perspective of any node, the universe looks approximately the same in all directions, and the speed of propagation is constant, mimicking the spacetime symmetry we hold so dear. We are left with a profound new image of reality. The vast, empty space between stars is not truly empty. It is a fossil, a relic of a broken connection in a graph that encompasses all of existence. We are not living in a continuous arena, but on the stable surface of a cosmic crystal that formed in the first instance of time. The geometry of reality might be simpler than we ever dreamed. A recent breakthrough in theoretical physics has revealed a stunningly beautiful object known as the amplituhedron. This is not a shape that exists in our familiar three-dimensional space. It is an abstract, multi-dimensional geometric form whose properties are rewriting the rules of quantum physics. Its discovery emerged from a frustrating puzzle. For decades, calculating how subatomic particles scatter after high-energy collisions was a computational nightmare. Physicists relied on a method involving thousands of intricate Feynman diagrams, each representing a possible path the particles could take. These calculations were not only brutally complex, but they also involved adding and subtracting vast quantities that individually blew up to infinity, only to cancel each other out at the very end to yield a sensible, finite answer. It was a process that worked, but it felt clumsy, inefficient, and deeply unnatural. The amplituhedron changes everything. Researchers found that the final answer for these particle scattering amplitudes, the ultimate probability of a collision's outcome, is not the result of a tedious calculation. It is simply the volume of this special geometric shape. Imagine needing to know the area of a circle. Instead of measuring its radius and squaring it and multiplying by pi, you are simply given the circle itself. The area is an inherent property of its form. The amplituhedron works in the same way for the outcomes of particle collisions. This geometric shortcut is more than just a mathematical convenience. It is a profound clue about the nature of reality. The traditional framework of quantum mechanics rests on two sacred pillars, locality and unitarity. Locality is the principle that particles can only interact if they are at the same point in space and time. Unitarity is the rule that probabilities for all possible outcomes of any event must always add up to 100%, ensuring the conservation of information. The entire machinery of Feynman diagrams is built upon these two assumptions. Yet, the amplituhedron calculation produces the correct answers for particle interactions without any reference to these principles. It does not use locality, and it does not use unitarity. They are not inputs into the geometry, they are outputs that emerge from it. This suggests that locality and unitarity, the very bedrock of our quantum world, may not be fundamental features of the universe. They could be approximate, derived concepts that only appear in the low-energy world we inhabit. The amplituhedron hints that a deeper, more pristine geometric reality exists, and our perception of particles moving through a spacetime arena is a secondary, almost illusory consequence. This geometric object points toward a quantum spacetime where the familiar notions of cause and effect, of here versus there, dissolve into a more fundamental and perhaps more beautiful mathematical truth. The ghost that haunted massive gravity for decades was its own instability. For a long time, any attempt to give the graviton a mass seemed doomed. Theorists David Boulware and Stanley Desir uncovered a fatal flaw in such models, a pathological instability that came to be known as the Boulware-Desir ghost. This was not a spectral apparition, but a mathematical phantom, a field with negative kinetic energy that would allow the universe to create infinite amounts of energy from nothing, completely destroying causality and stability. It was a deal breaker, a sign that a massive graviton was fundamentally incompatible with a sensible universe, but physics has a way of reviving dead ends. A breakthrough came in the 21st century when physicists constructed a new, ghost-free theory of massive gravity. The key was a clever mathematical structure that acted like a set of cosmic constraints, carefully taming the unruly degrees of freedom that would otherwise spawn the destructive ghost. For the first time, it seemed possible that the graviton, the hypothetical messenger of gravity, could have a tiny mass without ripping the fabric of reality apart. This opens up a profound possibility. If the graviton is not massless, then the gravitational force must behave differently over immense distances. In Einstein's general relativity, a massless graviton means gravity has an infinite range, stretching across the entire cosmos to bind galaxies in clusters. But a massive graviton would be different. It would imply that gravity, like all other forces with massive carriers, has a finite range. Beyond a certain cosmic scale, the gravitational pull would weaken much more rapidly, effectively cutting off. This modification to the law of gravity on the largest scales could provide a perfect explanation for the accelerating expansion of the universe. We would not need a mysterious dark energy pushing galaxies apart. Instead, the weakening of gravity's grip over vast intergalactic distances would naturally allow the universe to fly apart faster and faster. The force that holds our solar system together would be slowly fading on the grandest stage of all. The hunt is now on to find evidence for this minuscule mass. Since the graviton is so feeble, its mass would be unimaginably small, but not zero. Scientists are looking for its signature in the faint ripples of gravitational waves. A massive graviton would travel at a speed slightly less than the speed of light, and different frequencies of gravitational waves would be affected differently. By comparing the arrival times of these ripples from cataclysmic events across the universe, we might one day detect a telltale delay, a whisper that the cosmic glue binding our reality has a little bit of weight after all. This staggering failure of prediction is known as the cosmological constant problem, and it stands as the most embarrassing discrepancy in all of modern science. Quantum field theory, our most successful framework for describing particles and forces, makes a straightforward calculation about the energy of empty space. It adds up the contributions from every quantum field's fluctuations, a seething sea of virtual particles constantly popping in and out of existence. The result is a number of such immense density that it should be curving the universe into a microscopic, hyper-dense ball. Yet our actual observations of the cosmos reveal a universe that is vast, flat, and expanding at an accelerating rate, driven by a force we call dark energy. The measured value of this dark energy, the cosmological constant, is not just a little bit smaller than the prediction. It is over 120 orders of magnitude smaller. To grasp the sheer scale of this error, the difference between the theoretical prediction and reality is greater than the difference in size between a single proton and the entire observable universe. It is the worst theoretical prediction in the history of physics, a screaming signal that we are profoundly missing something. This is not just a problem for cosmology, it is a core problem for quantum gravity. The vacuum energy is a property of spacetime itself, a marriage of quantum mechanics and general relativity. To resolve the paradox, we need a theory that can tell us how the quantum foam of the microscopic world averages out to produce the serene, nearly flat geometry we observe on cosmic scales. Why is the energy of the void so close to zero, but not exactly zero? One controversial solution is the anthropic principle. This idea suggests that the value of the cosmological constant is not determined by a unique mathematical formula, but is instead one of many possible values across a vast multiverse. In most of these universes, the cosmological constant is enormous, and those universes either collapse instantly or fly apart so quickly that no stars, planets, or life can ever form. We find ourselves in a universe with an exceptionally tiny cosmological constant, not because it is mathematically special, but because it is one of the rare islands in the multiverse where the conditions are just right for observers like us to exist. String theory provides a potential mechanism for this with its landscape of vacua. The theory suggests there are perhaps 10 to the 500 or more distinct ways to curl up its extra dimensions, and each of these configurations corresponds to a different universe with different physical laws, including a different value for the cosmological constant. Our universe is simply one leaf in this cosmic jungle, its properties selected by our own existence. For many, this is a deeply unsatisfying retreat from the traditional goal of physics to find a single, elegant explanation for our universe. It trades a fundamental calculation for a statistical accident, yet it forces us to confront a haunting possibility. Perhaps the deepest constants of nature are not dictated by beautiful equations, but are merely local environmental conditions in an infinitely varied cosmic landscape. Time itself may be the final, most stubborn barrier between our two great theories of reality. General relativity treats time as a dynamic actor, a flexible dimension that can stretch and warp under the influence of matter and energy. It is a player in the cosmic drama, not merely the stage, yet quantum mechanics requires a rigid, external clock that ticks away in the background, an absolute reference against which the probabilities of particle interactions unfold. This is not a minor disagreement, it is a clash of worldviews at the most fundamental level. The conflict becomes starkly clear in the Wheeler-DeWitt equation, a profound result from early attempts to quantize gravity. This equation describes the entire cosmos in a single, breathtaking formula, but with one shocking omission. The variable for time simply vanishes from the mathematics. It presents us with a static, frozen picture of the universe, a timeless block where nothing ever happens. How can this be reconciled with our direct experience of a flowing, changing present, where causes lead to effects and the future is genuinely unknown? One audacious proposal is the concept of a wave function of the universe. Just as the wave function of an electron describes its probabilistic state across all possibilities, this grander wave function would describe the probability of different three-dimensional geometries for the entire cosmos. In this view, the universe does not evolve in time, it just is a vast landscape of possible configurations. Our perception of time's flow would then be a kind of cosmic mirage. But how does such a powerful illusion arise? The answer may lie in the intricate web of quantum connections. Think of the universe not as a single object, but as a collection of countless subsystems. Your body is a subsystem, the device you are using is another, the planet Earth is a vast one. None of these systems are truly isolated, they are all entangled with each other. Time in this emerging picture is not a fundamental background. It is a story that is told by the changing correlations between these subsystems. When one part of the universe interacts with another, their quantum states update in relation to each other. It is this relentless process of correlation that creates the orderly sequence of events we experience as the past leading to the present and flowing into the future. You can think of it like a movie. The film itself is a complete static object with every frame already existing. This is the timeless perspective of the Wheeler-DeWitt equation. But the experience of watching the movie, the unfolding story with its drama and suspense, only happens because the projector illuminates one frame after another, creating a narrative from the still images. In our universe, the projector is the network of quantum correlations. Your consciousness, constantly correlating with your surroundings, acts as the readout mechanism that gives you the powerful, undeniable sensation that time is passing. This means the river of time we feel so deeply might be the current of quantum information flowing between the countless parts of the cosmos, a cosmic computation that writes the story of reality as it runs. This paradox of incineration versus peaceful descent demands a more elegant solution. Black hole complementarity offers a profound answer rooted in the very nature of observation itself. It proposes that the experience of an astronaut falling into a black hole and the perception of a physicist watching safely from afar are not contradictory. They are both perfectly valid, complementary descriptions of reality, much like how light can be both a particle and a wave. You can measure one behavior or the other, but you can never capture both natures in a single experiment. The universe, in its deepest workings, seems to respect this principle of perspective. For the astronaut crossing the event horizon, the journey remains serene. There is no firewall, no wall of energy. The horizon is not a physical barrier, and they pass through it without incident, following the smooth, curved spacetime of Einstein's general relativity. From their point of view, all the information that made up their body and their ship continues its journey inward, untouched and unscrambled. Yet, for the outside observer, something entirely different happens. Due to the extreme gravitational time dilation, they would never actually see the astronaut cross the horizon. Instead, the astronaut would appear to slow down, fading and reddening until their image is smeared across the black hole surface. All the information about the astronaut is not lost inside. According to the laws of quantum mechanics, it is meticulously encoded onto the event horizon itself, a process known as quantum scrambling, and is then slowly radiated back out as Hawking radiation. So, is the information destroyed inside or preserved outside? Complementarity makes a startling claim. It says both are true. The information passes through the horizon for the infalling observer, and it is reflected at the horizon for the distant observer. This is not a logical error because no single observer can ever be in both places at once to witness the contradiction. The laws of physics conspire to prevent any experiment from revealing the paradox. If you tried to prove the information was both inside and outside, you would find it is impossible to collect the evidence without destroying the information yourself. This principle protects the core tenets of both quantum mechanics and general relativity by acknowledging that reality is, in a sense, observer-dependent. The complete truth about a black hole is not a single story, but a collection of all possible stories from all possible viewpoints, and these stories are stitched together in a way that forbids any one observer from seeing the seams. It suggests that the universe's most violent paradoxes are not flaws in its design, but merely limitations of our own point of view. The seeds of our cosmic home were sown in a realm beyond physics. Every galaxy, every cluster of stars we see today can trace its lineage back to microscopic quantum fluctuations in the fiery dawn of time. These tiny ripples were stretched to astronomical sizes by the universe's rapid expansion, eventually becoming the gravitational wells that pulled matter together into the vast structures we observe. But this triumphant story of creation contains a deep and troubling paradox. If we follow this process backward, rewinding the cosmic film to the first instance after the Big Bang, we find these seed fluctuations being squeezed to impossibly small scales. Their wavelengths would have become far smaller than the Planck length, the fundamental limit where the very concepts of space and time are thought to lose all meaning. This is the trans-Planckian problem. It reveals that our most successful model of the early universe, cosmic inflation, is built upon a foundation that ultimately crumbles. We are using the physics of the large, classical world to describe a regime where only a theory of quantum gravity can possibly apply. It is like using the rules of continental drift to describe the movement of a single grain of sand. The problem forces us to confront a stark reality. Our entire cosmic history, from the largest galaxy to the smallest planet, may have been dictated by physics operating in a domain we simply do not understand. How can we trust our origin story if its first chapter is written in a language we cannot read? One potential solution is to introduce a cutoff, a fundamental limit to how far back we can project our current physics. Imagine inflation not as a process that stretches pre-existing quantum fluctuations, but as a mechanism that actually generates them from the fundamental graininess of spacetime itself. In this picture, the universe does not probe distances smaller than the Planck scale because such distances do not exist in a meaningful way. The quantum foam of theories like loop quantum gravity could provide a natural cutoff, a point where the smooth fabric of spacetime dissolves into a discrete network, preventing wavelengths from shrinking into the nonsensical trans-Planckian domain. The fluctuations that seeded our universe would then be born from the intrinsic vibrations of this quantum geometry, their properties imprinted by the fundamental structure of reality rather than by a mysterious initial condition. This transforms our view of the cosmos. The largest structures in the universe become direct fossils, not just of an ancient inflationary field, but of the quantum nature of spacetime itself. The pattern of galaxies in the night sky could be a colossal echo of a time when space was not smooth, but a seething, discrete tapestry. Stephen Hawking's initial victory for general relativity was a stunning blow to quantum mechanics. His calculations showed that black holes are not truly black. They glow with a faint heat now known as Hawking radiation. This radiation is not a product of the star that collapsed, but is created directly from the gravitational energy of the black hole itself, right at the edge of its event horizon. Pairs of virtual particles which constantly flicker in and out of existence in empty space can be torn apart by the black hole's immense gravity. One particle falls in while the other escapes, carrying away a tiny bit of the black hole's mass. Over eons, this process causes the black hole to slowly shrink and ultimately evaporate, vanishing from the universe in a final burst of radiation. The problem lies in the nature of that escaping heat. Hawking demonstrated that this radiation is entirely random, purely thermal, and carries no information about what fell into the black hole. It tells you nothing of whether the black hole was formed from a collapsed star, a cloud of dust, or a library of encyclopedias. When the black hole finally disappears, all that intricate information about its history seems to be permanently erased from reality. This is the heart of the information paradox. Quantum mechanics holds the principle of unitarity as sacred, a rule that demands information must be preserved, never destroyed. It can be scrambled, hidden, or encoded in impossibly complex ways, but it can never truly vanish. Hawking's result was a direct violation of this foundational law, creating an impossible choice between two pillars of modern physics. The debate raged for decades, with Hawking famously betting other physicists that information was indeed lost. Then, in a dramatic turn of events, he conceded. After 30 years, Hawking announced he had been wrong, declaring that information does, in fact, escape a black hole. But how? The question shifted from if to how. The leading candidate is Hawking radiation itself. Perhaps the radiation is not completely random and featureless after all. The process of evaporation might be subtly encoding the information of the black hole's interior into the pattern of the outgoing radiation, like a cosmic ticker tape printing out the history of everything that fell in. This encoding would be so complex and scrambled that it would appear random to any observer, but the information would, in principle, be recoverable. Another elegant mechanism is the ER equals EPR conjecture, which weaves a solution from the fabric of spacetime itself. If every particle of Hawking radiation is connected to the black hole's interior by a microscopic wormhole, then information has a secret tunnel to escape through. It never needs to cross the event horizon in the classical sense. It simply takes a geometric shortcut, ensuring its preservation. Yet, for all these brilliant ideas, a complete and universally accepted resolution remains elusive. Each proposed solution pushes the problem one step deeper, revealing that to truly understand the fate of information in a black hole, we must first possess the final theory of quantum gravity. The paradox stands as a monument to our ignorance, a cosmic riddle ensuring that the silent fade of a black hole is anything but simple. This vast collection of possible universes is known as the string landscape. The theory's celebrated elegance, which once promised a single, unique description of reality, now points to a dizzying cosmic democracy. The specific way its extra dimensions curl up into Calabi-Yau shapes does not yield one perfect answer. Instead, mathematicians have discovered a staggering number of stable configurations, a number so large it defies human comprehension, perhaps 10 to the power of 500 distinct possibilities. Each of these configurations represents a different vacuum state, a unique universe with its own set of physical laws. In one universe, the electron might be heavier, making chemistry impossible. In another, the strong nuclear force could be too weak to bind atomic nuclei, preventing stars from ever igniting. Our universe, with its specific, life-permitting constants, is not a special creation. It is simply one ticket in a cosmic lottery of unimaginable scale. This landscape provides a direct, if controversial, solution to the cosmological constant problem. Why is the energy of empty space so inexplicably small? The answer, according to this view, is that in the overwhelming majority of universes it is not. In most of the landscape, the vacuum energy is colossal, and those universes are stillborn or tear themselves apart instantly. We find ourselves in a universe with a tiny cosmological constant for the same reason we find ourselves on a planet with liquid water and a stable atmosphere. It is one of the rare habitable corners of a much vaster reality. This is the anthropic principle in its starkest form. Our existence acts as a selection effect, filtering our observations to only those environments capable of supporting life. For some physicists, this is a profound and necessary insight, a humbling acknowledgement that our universe is not the center of creation. For others, it is a deeply troubling retreat from the traditional goal of science. The fear is that if a theory can predict everything, it ultimately predicts nothing. If any value for a physical constant can be explained by saying it exists somewhere in the multiverse, then the theory loses its power to explain why our particular universe is the way it is. The string landscape has ignited a fierce debate that cuts to the very heart of what physics is meant to accomplish. Are we searching for a unique, elegant theory of everything, or are we cosmic archaeologists merely cataloging the local conditions of our own accidental pocket of reality? The landscape stands as both a promise and a warning, a vision of infinite possibility that risks leaving our own world feeling strangely random and unexplained. Beneath the serene geometry of our universe lies a state of pure chaos. At the unimaginably small Planck scale, the very stage of reality dissolves into a seething, turbulent froth known as quantum foam. This is not a metaphor. The uncertainty principle, which prevents us from knowing both a particle's position and momentum, applies with terrifying force to spacetime itself. Empty space is not truly empty, but a maelstrom of violent fluctuations. Here, the concepts of distance and duration lose all meaning. For fleeting moments, the fabric of reality contorts into microscopic black holes and wormholes, which spontaneously pop into existence and then vanish just as quickly. It is a turbulent sea of geometry, constantly bubbling and boiling at the foundation of everything we know. This quantum foam represents the ultimate graininess of space-time, a pixelated underworld revealed only at energies we can scarcely comprehend. Different theories offer their own visions of this chaotic realm. Loop quantum gravity describes it as a dynamic spin foam, a complex, evolving web where the loops of space constantly reconnect and change. String theory, in contrast, pictures the foam as a consequence of strings and branes interacting in the hidden dimensions, their vibrations stabilizing the froth. Imagine a pot of water at a furious boil. From our macroscopic perspective, the water's surface looks smooth and calm. But if you could shrink down to the molecular level, you would see a frantic dance of collisions and bubbles, a chaotic frenzy that defines the liquid's true nature. Our smooth, continuous spacetime is that calm surface, while the quantum foam is the underlying, turbulent reality. This is the hidden engine of the cosmos, a churning ocean of potential from which all structure emerges. A black hole is the universe's ultimate paradox, a cosmic object defined by its ability to erase information from existence. Yet a profound discovery revealed that black holes are not the featureless prisons they appear to be. They possess a staggering amount of entropy. In the 1970s, physicist Jacob Bekenstein made a revolutionary connection. He realized that a black hole's entropy, which is a precise measure of its information content or hidden disorder, is not proportional to its volume as logic might suggest. It is exactly proportional to the surface area of its event horizon. This was a clue of monumental importance. In any normal system, like a box of gas, the maximum possible entropy grows with the volume. A larger box can hold more molecules and therefore more possible arrangements, more hidden information. But a black hole, the most efficient information compressor in the cosmos, defies this fundamental rule. Its capacity for disorder is defined not by how much space it encloses, but by the area of its boundary. The Bekenstein-Hawking entropy formula is deceptively simple. It states that the entropy is 1/4 of the horizon area measured in Planck units. This equation is more than just a calculation. It is a signpost pointing toward a deeper reality. It implies that all the information about what fell into the black hole, every atom, every star, every bit of history, is not lost within the vast, dark interior. It is somehow painted onto the two-dimensional surface of the horizon. The three-dimensional interior is, in a sense, redundant. The real description of the black hole's contents lies on its boundary. This stunning insight was the seed that later grew into the full holographic principle, the idea that our entire three-dimensional universe might be a projection from a two-dimensional information field at its edge. Any theory that claims to be a complete theory of quantum gravity must be able to explain this mysterious formula. It must answer a simple but profound question. If the entropy counts the number of microscopic quantum states hidden inside the black hole, what are those states? What are the fundamental atoms of spacetime that store this information? String theory provided the first successful microscopic count. It describes certain black holes as a tangled web of strings and branes, the theory's fundamental object. By calculating the number of different quantum configurations these strings and branes can assume, string theorists were able to derive the exact Bekenstein-Hawking area law from first principles. The vast surface area of the horizon was simply counting the number of ways these invisible, vibrating strings could be arranged. Loop quantum gravity achieved a similar triumph from a completely different starting point. In this theory, space itself is a woven fabric of tiny, quantized loops. When applied to a black hole, the theory predicts that the event horizon is pierced by these fundamental lines of space, each carrying a tiny bit of area. The entropy of the black hole is then calculated by counting all the different ways these lines can puncture the horizon without changing its total area. Again, the result precisely matches the famous formula. The The fact that two vastly different approaches can both reproduce this fundamental law is a powerful hint that they are touching upon a universal truth. The Bekenstein-Hawking entropy is not just a property of black holes, it is a fundamental limit on how much information any region of space can possibly contain. It tells us that reality at its deepest level might be far simpler and more two-dimensional than it appears. A quantum particle can feel a ghostly presence where no force exists. This strange phenomenon lies at the heart of the Aharonov-Bohm effect, a cornerstone of quantum theory first discovered in the realm of electromagnetism. Picture a long, hollow metal cylinder with a magnetic field carefully confined entirely inside it, completely shielded from the outside. In the space outside this cylinder, the magnetic field is precisely zero. If you sent an electron flying through this field-free region, classical physics would predict it travels in a straight, undisturbed line, completely unaware of the hidden magnet. But the quantum world defies this simple logic. The electron, behaving as a wave, is subtly influenced by the electromagnetic potential, an abstract field that exists even where the magnetic force is zero. This potential leaves a ghostly imprint, shifting the electron's quantum phase and creating a detectable interference pattern, as if the particle remembers a force it never directly felt. It is a stunning demonstration that in the quantum realm, potentials can be more fundamental than forces. Now, physicists ask a breathtaking question. Could gravity possess a similar ghostly counterpart? The gravitational Aharonov-Bohm effect proposes that a quantum particle, like a neutron or an atom, could be influenced by a gravitational potential even in a region of perfect zero gravity. Imagine a massive, rapidly rotating spherical shell. According to general relativity, the spacetime inside a perfectly symmetric rotating shell is flat, meaning an object inside would experience no gravitational forces, no tides, no curvature. It would be a gravity-free vault, yet the gravitational potential generated by the shell's rotation, a phenomenon known as the gravitomagnetic potential, would still permeate the interior. If you could split a beam of quantum particles and send one part through this gravity-free interior while the other travels outside, the two beams might reunite with a shifted phase, creating an interference pattern. This shift would be a direct signal, a whisper that the particle has sensed the quantum nature of the gravitational potential itself. It would mean that gravity, like electromagnetism, has a quantum soul that can reach out and touch matter even from a place where its classical pull is entirely absent. The experimental challenge, however, is almost beyond comprehension. Detecting such an exquisitely tiny phase shift requires isolating the experiment from every conceivable vibration, every stray electromagnetic field, and every thermal fluctuation. It demands a level of precision that pushes the very limits of quantum metrology. But if such an experiment ever succeeds, the implications would be revolutionary. A positive result would provide the first direct experimental evidence that the gravitational field is a quantum entity, finally bridging the chasm between the worlds of the very large and the very small. It would prove that gravity, the force that shapes the cosmos, truly dances to the same quantum tune as everything else. Gravity might not be a local force. This radical idea challenges Einstein's core vision, where gravity's influence travels at the speed of light, warping the nearby geometry of spacetime in a smooth and continuous way. But in the quantum world, non-locality is a familiar ghost. Particles can be entangled, their fates linked across vast distances in a way that seems to defy any slow, local signal. What if gravity itself shares this spooky property, acting not just through the curves of nearby space, but reaching out across the cosmos in a single, instantaneous connection? This is the profound proposal of non-local gravity. By introducing this quantum behavior into the equations of gravity, physicists can resolve some of the most stubborn pathologies in our current theories. The dreaded singularity, that point of infinite density at the heart of a black hole, is a direct result of the local nature of general relativity. The equations break down because they demand that all effects propagate step by step through the fabric of spacetime. But if gravity is non-local, its influence is not limited to this slow crawl. Information about the entire mass of the collapsing star can be felt everywhere at once, preventing the matter from ever being crushed into an infinitely small and dense point. The singularity simply vanishes, replaced by a smooth, high-density region that no longer spells the end of physics. One of the most promising mathematical paths to this non-local vision involves rewriting Einstein's equations with infinite derivatives. This sounds complex, but the core idea is to allow the gravitational field at any point to depend on its value across the entire history of the universe, not just its immediate neighborhood. It is as if the force of gravity has a perfect memory, a holistic awareness of the whole cosmic system that prevents it from ever becoming unstable. These infinite derivative theories are exceptionally well behaved, free from the ghosts and infinities that haunt other approaches. They naturally smooth out the violent extremes, offering a universe where black holes have no central singularity, and the Big Bang itself might be seen as a transition from a previous cosmic phase, not a true beginning from nothing. This non-local character also provides a fresh perspective on the cosmos's accelerating expansion. The repulsive effect we attribute to dark energy could be a direct consequence of gravity's long memory. The vast, empty stretches of space are not truly empty. They are imbued with the non-local gravitational influence of all the matter that has ever existed, creating a gentle, pervasive push that drives galaxies apart. It suggests that the fate of the cosmos is written not in the local geometry, but in the timeless, interconnected web of gravitational memory. Our journey across these 30 theories brings us to the ultimate prize, a single, elegant framework that unites all of nature's forces. This is the dream of a final theory, a theory of everything. For centuries, we have known 3 of the 4 fundamental forces intimately. Electromagnetism binds atoms, while the strong and weak nuclear forces govern the atomic nucleus, holding it together or allowing it to decay. These 3 forces are beautifully described by the standard model of particle physics, a quantum theory of breathtaking accuracy. Yet gravity, the force that sculpts the cosmos, stands apart. Its refusal to be quantized is not a mere technicality, it is a profound clue. Gravity may not be a force like the others at all, but a deeper property of spacetime itself. This is the core of the resistance. The other forces play out on the stage of spacetime, but gravity is the stage. How do you apply the rules of the actors to the theater itself? Each path we have explored is a different answer to this dilemma. String theory suggests the stage is built from vibrating strings. Loop quantum gravity proposes it is a fabric of woven loops. Entropic gravity argues the stage is an emergent illusion. They are all attempts to find a common language, a set of principles from which both the stage and the players naturally arise. A successful unification would be the completion of a scientific quest that began with Isaac Newton. It would offer a single equation, perhaps simple enough to be written on a T-shirt, that describes every interaction from the frantic dance of quarks to the majestic swirl of galaxies. Such a theory would unlock the universe's greatest secrets. We could peer into the very first moment of the Big Bang, not as a singularity of infinite density, but as a transition we can understand and describe. We could know the ultimate fate of the cosmos and comprehend the true nature of black holes. It would reveal a reality far stranger and more interconnected than we ever imagined. A cosmos where every particle, every force, and the very fabric of space and time are woven from the same fundamental thread. The search for this final theory is more than a technical challenge. It is a journey to understand our own place in a universe whose deepest laws we are only beginning to grasp. From vibrating strings to the holographic illusion of space, these 30 paths reveal a cosmos far stranger than we ever dreamed. Each theory, whether it builds reality from loops, graphs, or pure information, is a testament to the audacity of the human mind, a daring attempt to read the universe's deepest blueprints. We stand at a unique moment in history, surrounded by a breathtaking diversity of thought, where the greatest minds on Earth are weaving mathematics and imagination into possible futures for physics. The absence of a single, final answer is not a failure but an invitation. This grand pursuit is stretching the very fabric of mathematics, forcing us to confront profound philosophical questions about the nature of time, existence, and reality itself. The ultimate theory of quantum gravity, when we finally grasp it, will not just be another equation in a textbook. It will be a key, one that can unlock the universe's most guarded secrets. It will tell us what sparked the Big Bang, what truly happens inside a black hole, and what destiny awaits the entirety of existence. This journey to the edge of knowledge is far from over. Tell us in the comments which of these incredible ideas captures your imagination the most, and subscribe to join us as we continue to explore the final frontiers of space, time, and thought.